conférence. Voilà.
Okay, got it. Okay, hi everyone. Well, thank you, Philippe, for the introduction, and thank you for the invitation. So yeah, I'm going to tell you about structures in the emission of protoplanetary disks. And so the idea is to discuss observation of protoplanetary disks. So I will tell you about these many structures that we see in protoplanetary disks, and we'll try to discuss what they can tell us about the origin of these structures. I mean, whether they can be due to the formation, the ongoing formation of planets forming in this disk. So I will discuss a couple of works that I've done in this area recently. And after this introduction, I would like to spend a little more time to tell you about a recent work that we have done about studying the observational signatures of eccentric Jupiters that form and finish their orbital journey in the gas cavity in a protoplanetary disk. So that's the plan for today. I have planned to talk about like 30 to 40 minutes, but if you have any questions on the way, it's definitely fine by me that you interrupt and ask any questions. So that's the plan for this afternoon. So switching slide now, so you should be seeing my second slide. And with the idea that now we have a fancy number of spatially reserved observation of protoplanetary disks. And what is very interesting is that it seems that structures, they seem to be just everywhere in the protoplanetary disk emission. So I'm showing you here a few examples of these that are observed in the dust continuum emission at radio wavelength. So this is obtained with ALMA radio interferometry observations. So you see there's a few examples of this where you can see, for instance, a sequence of dark and bright rings in the continuum emission. Again, this is at millimeter wavelengths. Sometimes the emission can be non-axis symmetric, so you get to see this sort of crescent-like structures, like in the second disk in this zoo of image, and even get to see some large-scale spiral structures in the dust continuum emission. So there's really a diversity of structures that we see in the disk continuum emission. This is true for the dust, but this is also true for the gas. I'm showing you here just a few examples that is taken from a large survey in gas observation. This is again obtained with ALMA. So this is showing again like a diversity of structures, like for instance here for this IM loop disk, you get to see what looks like a four-lobed structure where you get to see some tiny dips in the emission along the disk's minor and major axes. And again, you get to see rings, so dark and bright rings of emission, which can be either multiple, like in this disk, HD 163, which is, by the way, the same as the one that we've seen in the dust continuum emission over there, or sometimes just single rings of emission. So again, takeaway message here, diversity of structures that we see in the dust, that we see in the gas. And so the idea is to try and understand what's behind these many structures, what kind of dynamical signature this is telling us, and whether this has to do with planets. Again, we can also look at a given disk to try and get some further constraints by observing a given disk at different wavelengths and different beams. And this is what I'm showing you here with this MWC 758 disk, which is an interesting disk, which features a large cavity in the continuum emission. This is showing the disk here with ALMA at 0.9 millimeter wavelength. So you get to see the central star here, which is surrounded by this large cavity in the millimeter, which is about 40 astronomical units wide. And just outside this cavity, you get to see what looks like an eccentric, non-axis symmetric ring of emission, which passes by this structure here, which is denoted by clump 2 here in the image. And further away towards the northwest of the disk, you get another crescent-like emission, which is denoted by clump 1 here. So again, different structures that look again also differently when now you get to see the disk at a different wavelength. This is now showing the same disk, now imaged with sphere. So we see basically the disk at near-infrared wavelengths at 1.0 micrometer wavelength. So now what we see is the scattered light, the light scattered off the small sub-micrometer dust grains in the surface layers of the disk. So now we get to see quite a different picture where now we see some sort of large-scale spirals in the disk. So again, this is the thermal emission of the large dust particles that reside rather in the mid-plane structure in the disk. In the second image is now an image of what the emission looks like for this very small sub-micrometer dust particles in the surface layers of the disk. So again, it's really interesting to have this information to try and constrain the dynamical evolution of the small and of the large dust particles in a protoplanetary disk. And of course, we can also have some direct information on the gas, and this is shown here for the same disk. This is showing here the scene 18032 rotational emission, again in the sub-millimeter at wider wavelength with ALMA again. And now you get to see again something which looks quite different with an absence of emission in the central parts of the disk, just like the cavity in the top. And you have a non-asymmetric structure, which is quite different from the one that we see in the dust. So this is quite puzzling, but perhaps a point that I want to make here is that all these structures that we see in the dust or in the gas, the rings, the spirals, the cavities, I mean, they all look reminiscent of the kind of structures that we predict, that we see in hydrodynamical simulations of disk-planet interactions. And so this is what I'm trying to show you here with this image, which is obtained from an hydrodynamical simulation, which shows the surface density of the gas from such simulation. So the star would reside at the middle of this image. And so here there's a Jupiter mass planet, which is located here at 50 astronomical units from its central star. So we see the kind of structures that the planet triggers in this gas. I mean, we see some spiral density structures which are emitted from the position of the planet. You see that the planet also carves an annular gap around its orbit. So that's the blue structure that you see here where the gas surface density becomes quite small. And at the other edge of the planetary gap, you see some kind of non-axisymmetric structure, which is actually a vortex, which is due to the onset of an hydrodynamical instability that sets in this kind of disk-planet interaction simulation. This is the Rosby wave instability, and which is known for trapping dust particles differently according to their size. And so this is what you can see with all these tiny colored dots, which show the position of dust particles of different sizes, as you can see with the color bar on the right-hand side. So again, we see spirals, we see a gap, we see non-axis symmetric structures. So, I mean, somehow this is really reminiscent of the structures that I've shown you in the disk's emission, in the dust and the gas. So the question that I'm very interested in actually is to try and see what structures that we observe in actual disks that are actually indirect signatures of planets forming in this disk. Because actually, you know what? I mean, the issue is that except for this very disk that perhaps some of you are already familiar with, which is the disk around the PDS-70 disk, the drama that we have is that we do not see the planets directly when we image disks. I mean, we do not see like blobs or dots which say, yeah, there's a planet in there. So that's a big question. I mean, why, except so in this disk, the PDS-70 disk, why don't we see the planets directly? So by the way, if you're not familiar with these images, so this is showing the protoplanetary disk around PDS-70, as seen with a sphere on the left-hand side and with HALMA on the right-hand side. So this is a disk that has a cavity, which is about something like 40 to 50 astronomical units wide. And we see at least this emission here, which is emission coming from the circumplanetary environment, which is presumably arising from a planet which should be like a few Jupiter mass, approximately. This is this one here, 20 IU. And there's another structure here, which has to do with the second planet located a little further away. And quite interestingly, actually, when we look at the image with ALMA now, so we look at the dust continuum emission and radio wavelengths, we do see emission coming from the secondary planet, the one that is located slightly further away within the cavity, and we do not quite see emission coming from the vicinity of the innermost planet, which is actually quite puzzling and interesting for modelers like myself. So, well, so again, one issue here is why don't we see planets much more frequently in protoplanetary disk? And of course, a related, perhaps related question is if all the structures we see in this, I mean, have nothing to do with planets, then what else? So I must confess that I am on the planet team. So my research is directed towards trying and understanding the structures that planets can trigger in the protoplanetary disk, and to what extent the structures we see could be due to planets. So that's the kind of job that I do. And so here I'm just showing you one example of a study that we have done recently with a Chilean MSc student, Marcelo Barraza, where we try and propose an explanation for the different structures that I have already shown you for this MWC758 disk with a cavity, with the rings, with the spirals in the near infrared, which could be due to the presence of two massive planets that we don't see actually in the disk, but that we think could be responsible for the structure that we see. A first planet right here, which would be a Jupiter mass planet, which would be located slightly inside the edge of the cavity, and which would be mainly responsible for this eccentric non-axis symmetric ring of emission that you should be seeing with my pointer move. And another planet, a little more massive, located a little further away in the disk, and which would be responsible for this structure here with this crescent-like emission to the northwest of the disk. And you can see that this actually planet would be responsible for the spirals that we see in the near-infrared emission of the disk. So this could work, but of course, I mean, this raises lots of questions, because in this kind of models, I have to invoke the presence of quite massive planets, which would be like Jupiter mass planets located at a few tens of astronomical units. And of course, there are very interesting questions as to whether we do expect such planets to form easily in the protoplanetary disk or not. I mean, is it okay to assume that a 1 or a 3 Jupiter mass planet could form like at 80 or 100 astronomical units from a sun-like star, or even 2 solar mass stars? This is, of course, a challenging question. Moving on now with another point that I would like to make actually is that sometimes when sequences of dark and bright rings of emission are observed in the dust continuum emission, like for this disk around HL2, it's often argued that all these dark rings of emission could perhaps be due to planets actually forming in their disk. So with the idea that at the location of each dark ring of emission, you would have a planet with a different mass, which would explain the fact that here there's a slight under density of dust having to do with the planets moving, pushing the dust away from their orbit, and therefore implying a lack of emission in the dust continuum emission. So usually we have this idea that at each location of a dark ring, a planet with a mass of Neptune to Saturn, perhaps Jupiter, would be located. But most often when these studies are done, I mean, what they assume is that there's a planet in there, and we just assume that they are there, they do not move, and we look at the dynamical response of the disk and the disk continuum emission rising from that. But usually these disks are quite massive, and we do expect orbital evolution of planets to arise in this due to disk planet interactions. So here the point I want to make is that we have recently tried and see with my former PhD student, Gaylor Fernandez, what the implication of a migrating planet would be on the dynamics and on the thermal emission of dust in a protoplanetary disk. So this is like going a different route, like doing hydrodynamical simulation of these planet interactions, look at what the gravitational interaction of the disk gas would imply for the planet, so the planet would migrate over time, and look at the implication for the dynamics of the dust in a protoplanetary disk and what the emission would look like. So this is what I'm showing you here, where you can see on the left-hand side, the time evolution of the planet's orbital radius in our simulation. So we start with a Saturn mass planet, which is like at 20 astronomical units from a sun-like star. So the disk is initially quite massive. And for this kind of planet mass and for this kind of disk mass, we expect the migration of the planet to proceed quite rapidly towards the central star. And something that we have found, which is actually quite cool, is that the migration pattern of the planet doesn't have to be smooth or something which is like a continuous inward migration of the planet. The planet here appears to migrate like a staircase, like with several jumps along the way. And what we found is that at each time, actually, there's a jump in the migration process. There's actually interesting implication for the trapping of dust particles in structures caused by the planet. So let me go a little more into detail into that. So initially we have that Saturn mass planet that is sufficiently massive for that the spiral waves, the spiral density waves that the planet triggers in the disk to be shocks that try and move the gas and the dust away from the planet's orbit. So it's like a little bit like initially the planet would have an inner and outer dust ring just slightly outside of this orbit, which you can see actually on the right-hand plot, which shows the surface density, the perturbed surface density of the gas in black and white contours, alongside the position of dust particles of different sizes from 10 microns to 10 centimeters. So initially the planet would carve like a gap around its orbit with a pressure maximum just outside of its orbit, which traps those large dust particles in that particular first ring. And then as the planet moves inwards, then the planet would just push all the dust particles inwards of its orbit inwards, which is like the planet will snowplow the dust particles inward of its orbit until you see the planet migration accelerates here and then slows down. And whenever it slows down, at this location, the planet will create a new pressure bump just outside of its orbit where the dust particle will get trapped, second dust ring. And then again, the migration resumes. So the planet starts migrating then, poof, and then until the migration slows down again, and the planet will be able to make a new pressure bump, able to trap those particles again, and until the planet stalls its migration in the inner parts of the disk. So the idea with this scenario is that with a single inward migrating planet, we can actually create several dust rings with just a single planet that migrates in a discontinuous way. And so we predicted what the dust continuum emission would look like in this scenario. So this is shown actually in the left-hand plot, where you see a synthetic map of the dust continuum emission at 1.3 millimeters, and where you get to see this sequence of dark and bright rings of emission, which is just due to one planet migrating in the disk and not to several multiple planets, each being locating in the dark ring. So this is like an alternative scenario where, again, multiple structures, multiple ring-like structures in a disk could be due to a single planet that has migrating in the inner parts of its disk.
Clément, so, may I ask a question before you move on?
Antoine, please go ahead.
I was wondering why the migration is accelerating and slowing down. What's the physical explanation behind it?
Yeah, I had exactly the same question.
Oh, sure. So the fact that the acceleration of the migration in the first place, so that is a mechanism that is usually known as the type 3 runaway migration, and which is intimately related to the behavior of the gas in the co-orbital region of the planet. So that region of the planet that more or less shares the orbit of the planet and which triggers a torque, which is called a rotation torque. And as the planet moves through the disk, say that the planet moves inwards, part of the disk, which was located inward of the planet orbit, will just get trapped onto horseshoe U-turns with respect to the planet and be forced to be funneled through towards the outer disk. So it's like the planet forces the gas that was initially inward of its orbit to be shuffled, to be funneled towards the outer disk. So along the way, so the planet will lose angular momentum at the detriment of this outward migrating gas. And this is the engine, the driver of the accelerated inward migration. So this is the so-called type 3 runaway migration. But the thing is that when the migration accelerates, then it means that the planet and the gas will have a substantial relative velocity, which implies that the spiral density waves that the planet triggers in the disk gas becomes extremely strong shocks. So the physics behind this accelerated inward migration at some point will become different whenever the shocks that the planet triggers in the disk will be just too strong. So at some point, the waves that the planet generates in the disk become shocks that are extremely strong and which prevents that mechanism to be self-sustained, sorry. So that is the reason why at some point the migration needs to slow down, just because the shocks get too strong and the physics behind cannot just get away with that. And so it's like the same physical mechanism repeating again. It's like initially when the migration is slow, so the planet can migrate inward, and then the runaway type 3 migration gets into the game and accelerates the migration. And when the migration is sufficiently fast, then no way, the shocks say no, the waves say no, we cannot make that any faster, and so we have to slow things down. So things slow down, and then we repeat the same migration pattern again and again. And so that is why we get these several dust rings forming as the consequence of that migration pattern repeating itself over the migration journey of the planet.
Okay, thank you, super clear. Yeah, I'm wondering now, but maybe I'll ask later.
Okay, cool. Right, so moving on with, should finish my introduction at some point. The last point I wanted to make is that talking about indirect signatures of planets forming in disk, I mean, there's this interesting question as to whether we may be seeing planets in the gas emission of their disk via these velocity kinks in some particular channels of emission in the gas. So let me show you this example of an ALMA observation of this particular disk, HD97, where we see the dust continuum emission on the left-hand side. So we see a dark ring of emission, which is perhaps due to a planet. So that's why you get the sign circle here. And the same disk also observed with ALMA, but now in the 13 CO3 to 2 rotational emission, again in the sub-midnight. And when the emission is observed at a particular channel map, so at a particular wavelength of emission, if you wish, so we have this particular emission there, which looks like this butterfly-like shape, if you want. And you see that here on the right-hand side, this the wing of the butterfly, it's like broken. Oops, sorry, I switched slide. So you see here that the ring of the butterfly, it's like broken. There's discontinuity in the emission. And this discontinuity is something that is predicted to arise from the presence of shocks driven by a planet in a disk. So if you have no planet in a disk, the butterfly-like emission of the gas emission in the particular channel map is something which is very smooth, very continuous, like what you see on the right-hand side. And so indeed, when you do hydrodynamical simulations, what Christophe Pinte and collaborators did, well, you can actually not only, if you assume that there's a planet in the disk that could explain this dark ring in the dust continuum emission on the left-hand side, you get to also predict the kink in the gas emission. So again, this is perhaps the kink in the gas emission is perhaps yet another way of constraining the presence of planets behind the sort of ring-like structures that we also see in the dust continuum emission. So now that we have gone through the introduction, I will now present the second part of my presentation, which has to do with eccentric Jupiters in this gas cavity. So why is that? So the idea behind this work was to think about the possible origins for the warm eccentric Jupiters. So these warm eccentric Jupiters, they are the exoplanets that are highlighted by this red ellipse here in this diagram, which shows the planet to star mass ratio in y-axis as a function of the orbital period. We're just showing median values here, and the eccentricity is shown in color. So basically, these are these planets, typically in the Jupiter mass range, which orbit their star in more than 100 days. And so for which the median eccentricity is about 0.25, 0.3. And so there are interesting questions as to what is the origin of the eccentricity for these planets, because usually when planets form in a protoplanetary disk, the usual expectation is that planets would maintain a low level of eccentricity. So it's not quite clear actually that these eccentric warm Jupiters have something to do with protoplanetary disk evolution. But there are exceptions to this rule of thumb, and one such exception to the general expectation that planets would maintain a low level of eccentricity in their disk is if at some point planets would actually end up evolving in a low density environment in their protoplanetary disk, like some sort of a gas cavity in the protoplanetary disk. So you have a sketch of what I'm talking about. It's like the star is here. So you have a cavity which is essentially deprived of gas with a higher gas density content on the other side. And so the idea here is that the planet would initially form when there's plenty of gas. It would migrate inwards, getting closer to the star, and fall into the cavity. And at some point when the planet falls inside the cavity, it turns out that the magic of these planet interactions can actually rise and maintain the planet's eccentricity to a substantial level, which is what you can guess here from this result of simulation, where you see the time evolution of a planet's eccentricity and semi-major axis in one model that I will present you just from the next slide, where the planet forms slightly outside its cavity, like at 30 AU, moves inwards, maintains a low level of eccentricity, and from one point, the planet gets sufficiently far from the edge of the cavity that these planet interactions can successfully increase the planet eccentricity, which can be maintained to a substantial level, which is actually quite in line with the median eccentricity of the warm eccentric Jupiters. So this is something that we have recently revisited with Florian Debras and Jean-François Donati. And the idea that we had is that since we do tend to observe a lot of cavities in the protoplanetary disk emission, like in the dust continuum emission, but also as well in the gas emission. I mean, most disks with a dust cavity also happen to have a a decrease in the gas density within the cavity. So we asked ourselves, whether the presence of a cavity could perhaps be generic, could be due, for instance, to photoevaporation due to the central star, could be due to effects of magnetic winds, perhaps a combination thereof. So we think that there are plenty of good reasons to form cavities in protoplanetary disk, and we do tend to observe them quite often. So that led us to wonder whether this could be a generic way, perhaps, to form warm eccentric Jupiters in that protoplanetary disk. So with that idea in mind, then in this other study that we recently published this year, we tried and looked for the observational signatures that eccentric Jupiters would have in their disk emission. So let me tell you a little more about what we've done. So what we did was two-dimensional hydrodynamical simulations modeling both the gas and dust of a protoplanetary disk. The central star is a 2 solar mass star, and we assume that there's a 2 Jupiter mass planet that forms in the disk initially outside the cavity. The planet migrates inwards due to this planet interaction. The planet falls within the cavity, and then its eccentricity can rise, as I've explained you just before. Here we model the cavity in the gas via a radial profile for the disk turbulent viscosity, so the so-called alpha turbulent viscosity, which aims at modeling the turbulent radial transport of angular momentum in the disk, if we think that this is the main channel, the main route for the evolution of a disk gas. So this is the assumption that we make. So alpha is quite large inside the cavity, like a few percent, and reaches quite low value, few times 10 to the minus 4 in the outer parts of the disk. And this is usually something that we would expect if a cavity forms, for instance, if you have like photoevaporation going on, or another mechanism actually. What I'm showing you here on the left-hand side is what the gas surface density in the simulation looks like when the planet is still on a near circular orbit inside the cavity. So you see the planet is here. So we do see the spiral density waves that the planet triggers in the disk. And so the idea is that now that we know what the gas surface density looks like, we're gonna post-process the results of these hydrodynamical simulations with radiative transfer calculations and see what kind of emission we get in the gas. So this is what I'm showing you here. So I'm showing you here the 3 to 2 rotational transition of the 12 CO gas. So what we do here is that from the surface density of the gas in the simulation, we compute the number density of the 12 CO in our disk model, assuming some 12 CO to H2 number density ratio. And once we do that, we produce all the inputs for the radiative transfer calculations and so on and so forth. Here we get the specific intensity of the 12 CO emission when the disk is seen face on. So for now, I'm just assuming a low level of inclination, 0 inclination actually. We do not take photodissociation by UV radiation from the central star into account. And just for the time being, we assume a very small beam, as you can see here. So it's like the prediction that we have when we have like almost infinite angular resolution. It's just like the ideal case, just to see what kind of structure that we see. So perhaps you can see the planet, which is right here. So just look for the arrow. And so what you see is that it's pretty hard actually to really see clearly actually the planet structures. What's kind of interesting is that here you can see that the dotted curve shows the position of the cavity. And what you can see is that overall, the radial profile of the specific intensity of the 12 CO emission just smoothly decreases outwards. It's like if I was showing you the picture, assuming that it would be hard to guess that there's a cavity in the disk gas density with a jump in the surface density of the gas, which is by, say, 2 orders of magnitude at least. So this is due to the emission of the 12CO322 being mostly optically thick. So we are mostly sensitive to the gas temperature. But, you know, since we do see a little bit of structures in the disk, even inside the cavity, the emission is not entirely optically thick. It's like marginally optically thick. So that's why we get to see a little bit of structure in there. I forgot to specify that this distance is here, 100 parsec. And so moving on now, I mean, I'm showing you what we get when we take photodissociation into account. So photodissociation is taken into account by assuming that above some column density of the gas, so if the local column density of the gas falls below some threshold, like 10 to the 21 centimeters minus 2, then we assume that UV radiation can successfully deplete the gas density above that column. So that's how we take photodissociation into account, and you see that this changes a little bit the structures in the specific intensity, but not by a large amount. This is due to the fact that, again, the emission is quite optically thick still. Now, taking the inclination into account, so we basically see the same kind of structures as before. I'm just showing you before and after, but we do see this sort of four-lobe structure that I have already talked to you about, and which has to do now with the emission outside the cavity being optically thick. And as the disk is inclined with respect to the line of sight, we get to see emission coming
Sans que les porteurs du dossier jugent utile de prévenir le CNRS.
We do see the emission of the disk from the parts of the disk in front of the observer. More away from the observer. So that's how we get to see the four-lobe emission. And now if we convolve with the beam, which is larger, this is now a 50 milliarc-second beam, which is like the kind of beam or the kind of angular resolution we can get with ALMA disk gas observations. Now we get to see the planet emission is slightly visible there. We still see a little bit of the four-lobe structure that I've mentioned you about just before. And now if we add noise to the synthetic maps, which is done by considering white noise on the specific intensity prior to beam convolution, and with an RMS noise level, which is like, I mean, typical of what, again, we can reach with ALMA observations of protoplanetary disk gas, then this is the kind of structure that we see where overall we just see like a smooth, monotonically decreasing integrated intensity, and the planet emission is quite difficult to see. So this is like a little bit like the reference case, so that you have in mind what we would have when the planet would still be on a near circular orbit. And so the idea is just to show you by comparison what we get when the planet gets eccentric. So I'm going to show you the same set of slides, perhaps a little faster, now that you see the sequence of images that we're going to show you, just to show you the differences. So again, now I'm just showing you here on the left-hand side the surface density of the gas when the planet gets eccentric. So when it reaches an eccentricity of order 0.25. So now when the planet gets eccentric, it has a substantial velocity difference with respect to the background gas within the cavity. So it means that the spiral wakes of the planet become strong shocks again. And these shocks are sufficiently strong to move the gas around the planet's orbit. And the strong shocks can actually trigger some large density contrast for the gas inside the cavity. You can see here the planet, if you look at the density just above the planet and behind the planet, you can have a density contrast, which is like by a factor of 10. Which is a quite substantial contrast. And so the idea is, again, to see what this structure would look like in the gas emission. So again, showing you the 12CO322 synthetic emission, again, at an infinite angular resolution when the disk is in phase on and without dissociation. So we start to see a little bit of more structures in the synthetic emission, partly due to the fact that we allow for lower surface densities in the gas. You see here, the density is just 10 to the minus 3 grams per centimeter square, so that's really low. So it means that indeed the emission starts to become optically thin in some places within the cavity. So again, now if we plug in the UV photodissociation with the parametrization that I've shown you before, then the UV dissociation now can become quite effective and go down to the midplane of the disk. And so in that case, since we decrease the number density of 12CO by an arbitrarily large amount, then we can have actually extremely small specific intensity of emission in parts of the cavity where the density in the gas is actually smallest. Again, we look at what happens when we have a finite inclination of the disk with respect to the sky plane, and we convolve with a realistic beam size, so again 15 milliarc-second. And so now you see that this density contrast within the cavity takes the form of large-scale density intensity contrast in the 12CO specific intensity. So basically here, the blue part corresponds to this density depression that we have just underneath the planet, just below the planet in the azimuthal direction on account of the shocks, the strong shocks driven by the planet. I should emphasize that this particular density contrast or structure that we have here when the planet is actually near apocenter, we get the same kind of similar kind of structures when the planet is at a different orbital phase along its eccentric orbit. So when the planet is near periastron or something else along its orbit, we get to see a similar kind of contrast in the density in the gas and in the intensity for the 12CO. And again, now moving on with white noise superimposed to the specific intensity prior to beam convolution. So after the convolution, we get this observable intensity contrast due to the eccentric planet inside the cavity. So we can recognize the low density part of the gas inside the cavity just behind the planet in its azimuthal, along the azimuthal direction, and a relatively more intense part on the other side of the disk. So all in all, I mean, we think that this effect, I mean, this large-scale intensity contrast in 12CO322 is something that could be indeed detectable with ALMA. We played around with some other ways to modeling disk noise, gas noise, like with CASA, for those of you familiar with this. And I mean, simulating the gas emission like for 5-hour integration on source, I mean, we do get a very similar pattern in this synthetic map of gas emission. So we think that this is indeed really observable with ALMA. So another observational signature of the eccentric planet in its cavity is the fact that when the planet becomes eccentric in its cavity, not only the planet is eccentric, but the gas around the planet will also become eccentric. And this is something which leads to distortions in the isovelocity contours in the 12CO322 emission. So this is what I'm showing you here. So this is the synthetic velocity map obtained from a relative transfer calculation, post-processed from the simulations, with a few isovelocity contours. I'm showing you here what happens when the planet is still eccentric. So even with the presence of noise, I mean, we have like a fairly symmetric set of isovelocity contours in the disk. And whenever the planet becomes eccentric, so you should now be seeing an animated GIF. So you see that the isovelocity contours get shifted either rightward or leftward within the cavity. And this is to do actually with the gas becoming eccentric inside the cavity. So the gas is no longer Keplerian, it has a radial velocity component. And when calculating the velocity along the line of sight, we get this overall shift of the isovelocity contours in one direction or the other whenever the planet is eccentric. So that lack of symmetry in the isovelocity contours could yet be another way of pointing to an eccentric planet via the eccentric gas inside the cavity. I'm almost done actually, because I see that it's 10 to 5. I just have one piece of more information to give whenever the slide gets to the next one. Is that I have talked to you about the gas emission arising from our simulations. We also did model the dust evolution in our hydrodynamical simulations. And from the dust spatial distribution in our simulation, we also looked at the synthetic maps of the dust continuum emission. I'm not quite sure what you're seeing now because it looks like my presentation is sort of stalled, but hopefully you can still hear me. But I mean, nevertheless, I mean, what we found is that, well, that's what you see here. The result of simulation with the dust particles is what you can now see on the left-hand side. You can still see the gas with the black and white contours, and the colored dots show you the position of the dust particles. What you see is that basically all the dust particles will end up outside the cavity at some point because of radial drift mostly. And basically the takeaway message is that we do not find dust particles, a lot of dust particles left inside the cavity. And just outside the cavity, the dust particles are sufficiently far from the interior of the cavity where the gas is eccentric, where the planet is eccentric. So basically the dust particles outside the cavity, they just stay on nearly circular orbits. And for that reason, I mean, when you look at the dust continuum emission at 0.9 millimeter, you get to see an axisymmetric ring of emission at radio wavelength. So you would not guess from that particular synthetic image that there's an eccentric planet inside the cavity, just because the dust, again, they do not keep track of this eccentric motion inside the cavity. And the same is true actually for the small dust particles, so the very small dust particles, which are pretty well coupled to the gas overall, but for which inside the cavity, actually the level of the gas density is sufficiently low for the small dust particles, I mean below a few microns, to still undergo a substantial radial drift due to gas drag, because those small dust particles, they do have a Stokes number, which is actually not marginal, actually, due to the low density of the gas. And long story short, when we look at the synthetic map of the near-infrared scattered light emission, this is what you see on the right-hand side. Basically, we do not get to see significant emission from within the cavity, except perhaps from the circumplanetary environment, which is spotted by the white arrow. And so again, we basically see mostly emission coming from outside the cavity, and we would not guess that there's an eccentric planet inside the cavity. So the idea behind this last bit of information is to tell you that whenever there's a cavity in a protoplanetary disk gas, the fact that the planet can become eccentric or be eccentric inside the cavity is something that could really be spotted by the gas emission and not so much by the dust emission. So this is the main takeaway message. So you still have my conclusions in this slide. So I guess it's high time to ask questions if you have. Happy to answer any of your questions.
Thank you very much, Clément. That was brilliant. So the floor is open for questions now. I can maybe start with one. I'm not sure I'm getting, in order to, the mechanism to create the eccentric orbit of your migrating planet, it seems that in addition to having a cavity, you also have a continuously increasing dust density towards the outer region. Am I right? Or from looking at the left-hand side of the graph of the slide, not this one, but before the one with the gas density, I think it was maybe slide 20 or 16 or something. So is this consubstantial to creating, this, for instance, this one, it seems that the gas density is continuously increasing outwards, even outside the gap, it's increasing steadily.
You mean like the red part here?
Yeah, maybe it's even more. Maybe in the previous slide, the previous one where it was a bit smoother when it changed on the left hand side.
For the
Yeah,
case when it was.
yeah, but yeah, it seems that the gas density on the left hand side seems to, because gray is the densest, right?
That's correct. Gray is about 20 grams per centimeter squared. Yeah.
So you have a gap within 30 AU, but even beyond this, it seems that the gas density is increasing, right? Or am I missing something?
No, actually, I mean, it's reminiscent of the initial condition of the simulation where we have initially a density profile which is very, very shallow actually towards the outer parts of the disk. It might be
But
uniform.
shallow decreasing, not increasing, or
I mean, it's nearly flat. I mean, it's like the surface
okay,
density towards the outer edge, which is actually nearly uniform with our.
okay.
Which is
So
which is not
okay, so
actually
the gray color is basically your initial density which you have, and everything else is a departure from what you had initially.
not quite actually, because we have. I mean, when we do form the cavity in the gas via this jump in the turbulent viscosity, then to keep a roughly steady state of mass accretion within the disk, the surface density in the gas will also experience a jump in the along the radial direction. I mean, sort of, if you have like a jump of by 2 orders of magnitude in the alpha turbulent viscosity, you will have also a jump by 2 orders of magnitude in the surface density. So, I mean, you can think of the initial state of the simulation prior to the introduction of a planet as a sort of Heaviside density distribution, like with constant inside the cavity, and then you have the jump and constant outside the cavity, and with the density contrast between inside and outside the cavity, which is by 2 orders of magnitude, because that's the jump of alpha that we know.
And what is the width again of the cavity? I forgot the radial width of the cavity.
Sorry, you said the radial width of the cavity?
Yes.
So you mean like the range of radii for the transition between low and high level of density?
Yeah.
It's quite small actually. It's like of order the pressure scale height of twice the pressure scale height. So that's usually which is it has to be at least like a pressure scale height, otherwise it won't be would be physically weird. But it's pretty small overall.
Okay, thank you. Other questions, comments?
Yeah, I had another question concerning the first part where you're trying to create rings with this slow down and accelerating migrating planets.
Okay.
I was wondering, like, for instance, if you have an ALMA observation of beautiful narrow dust rings, then maybe from your model you could constrain something, because like I don't know what does it depend on, like how fast it migrates from one ring to the other. Does it depend on alpha, on the surface density of the gas? Is it something that you could constrain for a given system if you have the rings positions, for instance? Or, well, it's a naive question, but maybe that could be done. So I'm just wondering.
So I mean, something that you could, I mean, this mechanism so relies on fast type 3 runaway migration. So the occurrence of that regime of migration does depend on the gas surface density. So for that mechanism to occur, then you need a quite substantial surface density for the gas. So this is something that you could constrain for that mechanism to happen. And this is something which actually could be interesting if, I mean, if you see like a bunch of dark and bright rings, and if, for instance, in the dark rings of emission, you do not get any velocity kinks, that could perhaps point towards this mechanism, because if really you have one massive planet in each dark ring of emission, so you would expect the planet wakes to change the velocity of the gas to perhaps be visible like a velocity kink. So if at least the planet is massive enough, I think you can actually see that in the observation. So that's perhaps another way of thinking of the dark rings of emission. If we do not see any velocity kinks, perhaps that could be due to the fact that if you believe in the planet assumption, at least, that there's this continuous migration pattern with a single planet that took place. But again, that will require a massively large surface density for the gas. So that is something which could be actually confirmed or ruled out depending on the disk that we observe. If we can constrain the surface density of the gas or the disk mass from the observation, which is another issue.
Okay, great.
Okay. Any further questions?
I have one, if I may. So very nice talk, Clément. Yeah, I liked it. I was wondering, when you have an image like you showed at the beginning with two creation features, for instance, and then you manage to find where to put planets to reproduce the same image with the simulation. Do you have a rule to find where the planet should be to reproduce the features, or do you have to span all the parameter space and make many simulations to find one that looks like the image?
That's an excellent question. That's where I think you will definitely benefit from having multi-wavelength observations. If you just have, say for instance, say we consider that particular disk, right? MWC 758. If you just have the ALMA image on the top, then you have quite a substantial degeneracy in where you can put the planet and how massive you can have them. If you believe that that structure, which is denoted by clump 1 in the image, has to do with the planet which is located outward of that structure, then indeed you can have a range of planet masses and planet semi-major axes that can still make that structure out in the synthetic maps. However, the interesting thing is that for that particular disk, we have these spirals. And so for that particular disk, the information that we have on the location, the pitch angle of the spirals, was actually quite key in trying to say where the outer planet in the model should be. So there's always degeneracy in the modeling, but that degeneracy can be at least partly lifted with a combination of several observational data.
Okay, so then you use the second image to infer the semi-major axis of the outer planet, and then you made a simulation with that semi-major axis and be able to reproduce the pattern?
Yeah, actually, that's part of the story, indeed. Yeah.
Okay, so very nice. Yeah. And for the inner planet?
And for the inner planet, actually, I was I was expecting the question. For the outer planet, actually, the constraint can be quite different. Actually, it's also true actually for the outer planet, because there's something that you can also say about the observation is that we do not see planets, right? You don't see like a blob, like rising from emission from a circumplanetary environment or something like that. So this can this can actually tell you something about the typical or the upper mass that you can actually get away in the simulation. Like for instance, here I think I have like a 1.5 Jupiter mass planet in the simulation, like in the inner part within the cavity. But if I had taken like a 10 Jupiter mass planet, then or even larger, then presumably I would have expected significant thermal emission from the circumplanetary environment, and then I would have expected to perhaps to see the planet in the observations. So that's another constraint on the mass of the planets that you can actually use in the simulation.
Okay, thanks. And for the longitude of the planet, does it depend on the longitude of the planet, or is it related to the position of the pericenter, the clumps?
Not quite, actually. In the sense that, so those clumps, like for instance, this clump, we think it's due to vortex that forms in the gas and traps dust particles. But since the vortex here rotates at a different orbital velocity as the planet inside the cavity that triggers the vortex formation, it means that we cannot actually constrain the position angle of the planet just by knowing that of the clump in the observation. Unfortunately, we cannot constrain that. Something that can constrain actually the position angle of a planet if you have like this kind of spiral shaped structures. Also for the outer planet, that led us to constrain where the outer planet should be. But for that clump, for instance, for clump 2, for the planet inside of the cavity, no, not sufficient.
Okay, thank you.
Okay. Further questions? Okay. So if not, we thank again Clément. Switch back to French. Donc merci vraiment beaucoup. C'était le dernier Théminaire de cette année calendaire pour 2021. Donc pour les personnes qu'on ne va pas revoir, bonne fête à tout le monde. Et puis on se retrouve à la rentrée pour de nouveaux Théminaires. Merci à tout le monde.